the further we get away from our own solar system, the less we have certainty about in terms of our theories. And this class terminates in the final week in a discussion of cosmology. And we've been dancing around the idea of cosmology this entire course for the most part. But our cosmology is actually a relatively new situation. So all the way through the 1980s, I would say all the way through the 1990s, there was a considerable split in the cosmological community between a steady state cosmology, one in which galaxies are coming into being and disappearing, new matter is being made at the heart of galaxies and reformed and recycled, and one which is now called lambda CDM or Big Bang cosmology. And so your textbook focuses exclusively on the lambda CDM, which has been the most popular cosmology in the last 20 years, I would say. But it's also experiencing some serious challenges, and there's some contenders. Nobody has displaced it yet, but I want to work towards examining both of these cosmologies because I think they're quite interesting in opposition to one another. I think the best way that human beings can understand ideas is to look at two opposing, completely diametrically opposed ideas. And this is kind of the basis of Western dialogue and Western thought in general. You may have heard it called the Socratic method or something like this, where you have two different ideas and you have a conversation between the two of them. So that's what I want to work towards. But before we can get there, we need to look at a couple of interesting players in this discussion, which is what we're going to be doing this week. I think that we've covered all of the main astronomical bodies in the universe that we're aware of, or at least the different structures. We've made it through the stars. We've made it through these apparitions at the center of galaxies, these black holes. Talked a bit about that, what it could mean. And so today, and throughout this week, I guess, next time too, we need to look at the motion of these bodies, the motion of the galaxies. And this is a very tricky task because in order to understand motion, we have to understand distance. And at some points, we reach a distance beyond our own location at which our basic methods for gauging distance fall apart. And so the first thing that I want to do today is take apart all of our distance measurements and think about how we know what we know, because our cosmology depends on our ability to gauge extraordinarily long-range distances. And there's a great deal of uncertainty about that. There's this concept in cosmology called the distance ladder. And the distance ladder, we'll get to, I'll break it down for you, but the basic principle is that as you get further and further out into the universe, you're basing your estimates on earlier abstracted distances, which are based on earlier abstracted distances. And at some point, you get back to the basic direct distance measurement, which is looking at parallax, right? Beyond looking at parallax, which is, hopefully you guys remember this, but you're essentially, it's the thing where you point at something and close one of your eyes and close the other eyes. And because your eyes are at two different locations, you can triangulate the position of something. And this is why if you cover up one of your eyes for a day, you'll be stumbling all over the place and reaching past the cup on the table and things like this. Because it's very difficult to gauge distance without 2 points of reference. You need to triangulate it. Now, this is the only direct way that we have of gauging distances, but it only works for really nearby objects, right? It works fantastic, say, for a planet. But as you get further away, then you have to start considering things like Doppler shift. And Doppler shift is a way in which frequencies can shift and give you some estimate of distances. This is pretty useful for all sorts of techniques, radar speed gauges, right? I passed a couple of cops on the highway coming out here. They were making use of this technique. However, it's not the only way that frequencies can be shifted. And this obscures, this sort of blurs our ability to make definite statements about distance. And that's going to cloud our ability to make certain statements about long-range events. And so as we go through all of this, it's really important to understand that we are entering the absolute bleeding edge of what is known about the universe at this point. Now, this can feel a little bit dissatisfying, and I don't want to break anyone's hearts because we do understand a great deal about how the universe functions, but inherently that breaks down at some points. And we've reached a couple of these points so far in this class. I think black holes, which we'll keep talking about, and dark matter and dark energy are great examples of places in our understanding where there's gaps. And I think the appropriate way to approach these gaps is not with suspicion, but with excitement for the future and excitement for what can be done out there. I think that it's really important. I know that many of you will not become scientists. Most of you are from some other major field, right? But it's really, really important, no matter what field you go into, to recognize that if you want to make a difference in that field, whatever it is, say you go and join a new company, the most important thing to recognize is there's this concept called epistemic humility, which is at play in every endeavor that you'll undertake. And this is the basic idea that when you enter into an enterprise, there may be things you don't know, and you should recognize it when you go into it. If you even try to have a conversation with another person and you think that you know absolutely everything about what you're talking about, and you think there's no chance that this person has something to tell you, then the conversation will be miserable and a waste of everyone's time, because the person won't listen to you, and you're obviously not listening to them. And so I think that the principles that are playing out here in our cosmological discussion can be applied to your everyday lives as well. It's very, very important to take this grain of humility with every single aspect. As soon as you think you understand something, there's always something you don't understand as well. And it's absolutely critical to keep that in mind. Okay, so let's talk about distances a little bit. Let's talk about how we arrive at these very far-ranging distances, because I'm going to crack open the idea of the expanding universe, and your textbook does as well. And in order to understand why people have arrived at this seemingly bizarre conclusion, which we'll unpack, we have to understand why people think that these distances are increasing at a range. All right, so one of the first methods that we used beyond actually looking at parallax was looking at the Doppler shift of rotating binary systems. This is all well and good if you have a nice visible black binary system, but usually you don't. So one of the first momentous discoveries was that there were these very regular variable stars. They increased in brightness and decreased. These were called the Sepid variables. And these were used as something of a standard candle for a very long time. This was a big discovery in the early 20th century that, okay, if this thing is flashing like this over here, and it's flashing the same pulse way off there, then we can deduce its distance based on how faint that signal is, because it's clearly the same thing that's happening over here. This is a brilliant idea. It turns out that with some modification, the idea is quite useful as far as we know. But one thing that's really important to remember about this discovery is that when they first started applying the standard candle Sepid variable method to star systems, they had actually confused two different types of variable stars. And this led them to misapprehend the distances to those stars by as much as 2x. And so once they realized there was actually two populations of variable stars, they had to actually build that back into the theory and make a new method for discerning between the two. And I think that that's a really important lesson to remember, especially in terms of these extraordinary distances that we're going to move on, because the Sepid variables will take you out, I don't know, a few millions of light years. But the distances that we're going to be talking about here in a few moments is billions of light years into the past, into the distant past. Okay, so Sepid variables, a good lesson, and also a pretty brilliant revelation in its own right. People tried to improve on that, right? They wanted to be able to reach a little bit further. So they made the assumption that supernova were essentially also useful as standard candles. Supernova would be the same everywhere you looked. The brightness would fall off similarly, especially as we narrowed down the classification structure for supernova, and particularly type 1 supernova. This supernova standard candle idea reaches out. We can see supernovas that outshine entire galaxies, and they reach out billions of years. So this gets us a little bit further, but it's not quite far back enough, right? There's things we can see beyond these supernova, and we need a way to gauge their distance. And so that brings us to the point of redshifts, and we'll unpack that in a minute. But these are in terms of millions of light years, so 13,000 millions, 13 billion light years, which gets us very close to the edge, the limit of what we can see. And of course, the supernova get us further. We'll talk about the Talley-Fisher relationship in a minute. Not particularly sepid variables, and then the planetaries were much easier, right? Because they're nearby. So this is what we call the distance ladder for cosmology. This gives you a sense of how far each one of these different systems can lead us. Now, the possibility still remains that when we get into this supernova range, when we get into these very far off, beyond the Sepid variables, that we're actually looking at different types of supernova that we're not aware of. Remember, the decision to include all Sepid variables in the distance calculations originally was based on the assumption that the explosions that were near us, the pulsing stars that were near us were the same as the pulsing stars that were far away, and they turned out not to be the case. So one thing we never really know is whether what's happening near us is what's happening on the other side of the universe. It's a very, very difficult thing to make a statement about. We know that, for instance, if you go to, if you take a bus 4 hours to the east, you'll end up in a desert. If you go down to the South Pole, you'll be freezing, but you're still on Earth. So the conclusions that you might arrive at by standing in one place are not necessarily the ones that you're going to arrive at by standing in another place. And one of the fundamental assumptions of all of these cosmological models is that the universe is essentially the same everywhere. And I think this is a huge leap of faith, which we need to concern ourselves with in terms of ascribing certainty to what we're going to say today. And I know I'm going to sound a little bit like a broken record with all of this, but it's very difficult to stand in front of a class of people and tell them exactly what happened 14 billion years ago, because I don't think that anyone really knows the answer to that exactly. And so the best hope we can have is to look at the evidence for what we can see and then try to come up with different possibilities for what that could mean. And I really think that's the best way for science to unfold in general. So one thing that I'm going to reemphasize here is that at the base of the ladder here, we're making distance measurements based on direct observations, whereas everything that comes after it requires you to have some theoretical basis for the object that you're observing. In other words, if the thing that you think is a variable star is not a variable star at all, but it just looks like one, well, then you actually have no idea about the distance to it. And people recognize this. I'm not sure that really comes across in the textbook. This is an important piece of the puzzle, and it's an important part of the epistemological humility that we need to approach this subject with. By the way, epistemology, does anybody know what that means? I shouldn't use words like this. Anybody? Epistemology. So epistemology is the process by which we achieve knowledge, right? So the scientific method is a part of our standard Western epistemology, as is logic and rationality, right? These are ways that we process information in order to generate something that we call our modern knowledge base, let's say. So epistemological humility is having some sense of skepticism about the method that you use to achieve your knowledge base. And that doesn't often come across. And, I think that this happens for a reason. And this is something institutionally that we all have to think about in the future. People are obviously incentivized when you write a grant, when you launch a company, whatever it is, you're incentivized to have a great deal of confidence in your proposal because, well, no one's going to fund your company if you say, I don't know, it might work, right? So in some sense, it's very innate and very human for us to ascribe a great deal of certainty to our proclamations. But in reality, this is kind of works against us because it slows down the gears of progress. All right, so that's our distance ladder. Now, what about this expanding universe business? Now, I'm going to read you a quote from your textbook. We now come to one of the most important discoveries ever made in astronomy, the fact that the universe is expanding. Okay. What is a fact exactly, right? This is exactly the kind of language that I think is a little bit of a disservice to you. The universe is a concept, first of all, right? What does the universe mean? Well, in astronomical terms, it means what we can see. And what we can see certainly is expanding. That is absolutely true. In fact, it expands more and more the more we improve our telescopes, right? So this new telescope, this very expensive project, which we plopped in space to replace the Hubble, it's called the James Webb. James Webb can see further with greater resolution than the Hubble. So in a very real sense, the universe for us is certainly expanding, but this isn't exactly what what your textbook means by the discovery that the universe is expanding. Interestingly, when people first started looking at the spectra of distant galaxies, when people first realized that that the spiral nebula weren't part of our galaxy, and this was within 100 years, this is about 100 years ago. When people realized the universe was bigger than our galaxy, they started examining the spectra of these spiral nebula. And around the same time, the people who were studying this actually believed they were in the galaxy, and they were trying to understand the composition of these nebula because they thought they would be forming planets. Well, they turned out, of course, to be galaxies. And when they examined the spectra of these galaxies, they found that the spectra were shifted to the red, right? The frequencies were the wavelengths were all stretched out a bit. Now, people were puzzling over this for a long time. It was essentially, at that moment, scientifically speaking, science was very much, had set itself in opposition to religion. And so scientists saw themselves as vanquishers of superstition. This is actually a very different approach in some sense than we have today. And unanimously across the board, every single one of these astronomers stood behind an eternal version of the universe that was more or less cyclic and dynamic. It changed, but it more or less stayed the same. And so this revelation that galaxies appeared to be shifted red. In other words, they appeared to, by a Doppler perspective, be moving away from us, was very disconcerting. Now, the issue was brought to a head by this gentleman. This is Father Georges Lemaitre. And Lemaitre was a mathematician and a Catholic priest. Now, Lemaitre was analyzing the redshift data. Meanwhile, Hubble on the other side of the ocean was compiling even more and more of it and was making a catalog. And Lemaitre realized that if you took the redshifts of galaxies outside of ours, right, extra galactic systems, if you took those redshifts and you assumed that they represented a true recession velocity, they're moving away, that you could trace that recession velocity back to an original point. And of course, this gave, I'm sure, I mean, I'm inside the mind of the witness here, but I'm sure this was very satisfying to the Belgian priest, who immediately decided that this was proof for the creation moments of the universe, which of course is an age-old idea, which you find in almost every single culture going back tens and tens of thousands of years ago, right? Our earliest myths, our earliest stories, you know, this is why I took some time to go through these ancient star catalogs and the ancient myths a bit with you, because this idea that the universe had an origin moment, had an inception, is as old as humanity itself. And so when Lemaitre realized that the redshift data could be fitted to this story, he almost certainly felt like he'd struck gold. Now, the Pope was very, very excited about this paper, actually, and Lemaitre's findings. Lemaitre actually wrote several letters to the Pope telling him to shut up because it was making him look bad. So, you know, when Lemaitre first published this, actually, he was basing his ideas on the relativistic principles from Einstein's general relativity. Einstein actually was initially very, very unhappy about this because, again, he set himself very much opposed to the superstitious interpretations. How could something come from nothing, essentially? And this battle went on for a long time. I think that most history books gloss over this point, that the majority of the cosmological community was not quick to embrace this idea. And it actually took the discovery of CMB for most cosmologists to flip on the steady state model. And I'm going to break down the steady state model for you with great luxury of depth next week, hopefully, maybe even Thursday. So the principle here is based on Hubble's data, which looks like this. Okay, what you see here is essentially the redshift. Don't worry about the units for that, but essentially more redshift with recession velocity. And so what this actually tells us is that the things that are actually redshifted the furthest are moving away even faster than the things that are moving away that are close to us, which are moving away. Now, this is in some sense a quite remarkable finding. The conclusion from it, however, requires a bit more consideration. So, you know, the standard conclusion from this is quite fascinating because it goes back to relativity and general relativity, which I hope that we've beaten that horse enough, but it's going to keep coming up, so it's worth considering it. Now, this is the image from your textbook that's given, and this is the standard explanation that's given for this expansion business, because, there's two parts of science, right? First is observational. Let's see what's going on. Let's catalog it. Let's describe it, right? This is what relativity excels at. It produces a very, 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 very precise description of what is happening in terms of the motion of bodies with respect to one another. The thing that it doesn't do at all is explain why those things are the case. Now, popular media, popular science, Hollywood, everybody has tried to reify that description into an explanation. In other words, general relativity tells you that when a body has certain quality, let's say mass, that it changes the trajectory of other bodies. And the way that it describes that is in terms of the narrowing and the contraction of lengths, right? In other words, the bodies are moving because not because, that's the problem. The bodies move with respect to their locations, which is space, right? Space is a coordinate system of locations. So I think that it's a little bit unhealthy for us to think that saying distances are changing, space, distances, locations are changing with respect to matter, and to just put a stamp on it like this is a final story. Because what relativity tells us is that, yes, the distances change with respect to the motion of large bodies, but it doesn't tell us why they change, right? And so it's a little bit troubling to me that we see something like this in the textbook, which is meant to be an explanation. The idea that space itself is expanding is at the heart of the interpretation that's popular in our cosmology right now. And this, I want you to really think about what that means, because space is a concept. It's not a thing. It's not a body that has a surface, right? It doesn't have a pressure boundary that's capable of interacting with other things. Space is a concept, and the concept means location of a body with respect to other bodies. Now, the application of physical processes to an idea is a very foundational logical fallacy, and the philosophers are quite aware of this logical fallacy. They call it reification. Reification is when you mistakenly apply concretization to an idea. In other words, if I tell you, if I say something like my feelings for, say I'm having a conversation with my wife, and I'm like, my feelings for you are warped today, right? I'm applying a physical idea of warping an object, right? Deforming it to an idea like my feelings, right? And there's some poetic value in doing that. In other words, you can get some analogy of what that means. Like maybe I'm a little cloudy, maybe I'm upset about something. There's some information there for sure. But you're not making a physical statement at the end of the day, because your primary object of the discussion, the object part of the sentence, is not a physical body that is subject to physical processes. And the tragedy here, which has led us to all sorts of chaos in lambda CDM, is that we treat the idea of space, particularly the dynamic object of space-time, which is really a movie of positions changing of different bodies, we treat that as a physical body and we apply physical processes to it. And this is something of a terrible confusion which occurs. Anybody have any questions over that? Does that make sense? Anybody? Now, I understand that the warping of space and time makes for fantastic stories, and this is why I don't want to be a downer about this, because I do think that, for instance, clocks are affected by gravity, right? And this makes sense from a mechanical perspective. And I do think that distances and trajectories are affected by gravity. Again, if we have a mechanical conception of gravity, this makes sense, right? If objects are attached to one another, if the atoms are physically bound to one another at great distances, then it makes sense that their trajectories would change when they're associating with larger clumps of material. So the description of what's happening is absolutely valid. The explanation for why it's happening is not finished, and it needs to be finished. And this is absolutely what an advanced civilization will understand at some point. If aliens come here and visit us, they will absolutely understand that this is the case, and they will have a mechanism for what causes those trajectories to change, what causes those clocks to slow down. All right. Now, in terms of this redshift business, because the redshift data is compelling, certainly it does appear the case that things which are far away are redshifted. Now, when this first happened, actually, when it was first discovered, very few people leaped to the conclusion that the reason that distant things were redshifted was because they were receding. Now, of course, the story in hindsight, because this is the analysis that we've embraced, this is told as if this was always the case, but it couldn't be further from the truth. Actually, the initial conclusion when people realized that distant bodies were redshifted was that, oh, well, the light is losing energy as it travels across the vast regions of interstellar space, intergalactic space, right? Because perhaps you will recall that energy is proportional to wavelength, right? So, sorry, it's inversely proportional to wavelength. So as the wavelength goes up, the energy goes down for light, right? Now, the amalgamation of the different attempts to explain how light would lose energy was bundled into a group of hypotheses called tired light. And tired light was tried on. There was a number of different mathematical proposals for how this could happen. But almost unanimously, they all considered that the way light loses energy in our everyday experience is that it is scattered off of atoms as it travels, right? So let's say some sunlight comes through a cloud. The cloud might disperse the light in different ways. And of course, this has very much to do with the reason our sky is blue, for instance, due to this similar scattering interacting with the different ions in the sky, right? And the gases. And so the problem with scattering to explain the redshift is that scattering affects certain wavelengths more than others. However, when we look at really far off galaxies, we see that all the wavelengths are shifted to the red, not just a few of them. And so the scattering mechanism doesn't work. The light isn't just getting scattered by space dust and so forth. However, none of these models have a physical mechanism for light itself. And I think this is a really foundational element to examine here, because if you think about the way that light is taught in textbooks and discussed amongst physicists, it's treated as if, on one hand, it's a transaction that occurs between two atoms, but on the other hand, we don't really talk about what happens between the one atom and the next. We don't understand the mechanism by which one atom influences another atom. And if we don't understand that, then we probably aren't going to understand how light makes it from the sun through to us. Because even if light from the sun reaches us, which much of it does, and isn't scattered, because neutral molecules don't scatter light, well, they're still in the path of that light, okay? Now, what does that mean for if you have two atoms that are undergoing a transaction, right? This interesting torsional transaction that we call light. What happens if you plop an atom in the middle of it and it doesn't scatter the light? What happens? Well, we don't know exactly. We actually, our models just ignore the fact that there's that atom in the middle, and we say it's a neutral atom, it doesn't interact with it, right? So we just take it out of the equation completely. But I think that if we start to imagine the processes that those neutral atoms can actually do, they must interact with the light as it comes through. Now, they might not interact with in the sense of scattering, but I think that there's a lot of work to be done on exactly what is done there to the atoms, and is that an energetic transaction to some extent? Is there some sort of loss of energy as you relay through a neutral atom that might not scatter you? I think these are open questions that have to be addressed in the future, but I don't think they're going to be possible without first wrestling with the fundamental physical mechanism for light itself, which we don't really have in physics right now. And that's something really to think about. I don't know if any of you guys do this, but I spent a lot of time when I was younger just thinking about what exactly the sun is doing to my eyeball when I'm seeing it in the sky, right? And it occurred to me at a pretty young age that it must be touching my eye somehow. And I don't really understand the dynamics of that, but it's something worth pondering. All right. Now, that gets us caught up from our snow day a little bit. So we're going to move on to a discussion of galactic nuclei at this point. In particular, we're going to talk about these things called quasars, which are a particular type of galactic nuclei that's active. Your textbook doesn't really clarify this very well, but quasars are really just a particular form, one particular instance of active galactic nuclei. And we'll explain what active galactic nuclei are in a second. But quasars are essentially active galactic nuclei. It's a hard one to say. Active galactic nuclei, which are pointed at us. So we can get very nice radio signals from them. All right. So I think the reason that we're taking a break from the expansion concepts to contemplate active galactic nuclei is to reiterate the fact that geologists, cosmologists, astronomers in the early part of the 20th century and beforehand were striving for a model of the universe that was predictable and constant, reliable. And very, very recently, this proposal, as we've seen already in many of our discussions, particularly about planetary formation and so forth, this proposal became untenable to some extent. And so people started moving away from this idea that galaxies just formed billions of years ago and then sort of slowly evolved within them and aged and died. And one of the key players in rewriting that history was the discovery of these quasars. And so the question that I hope we can answer today is well, I don't know that we'll be able to answer it, but I'm going to try. The question is, what is happening at the center of galaxies? Because something extraordinarily energetic is occurring there. And it's our job as scientists to make sense of it. So we'll look at quasars, this special case, the first hint that there was something insane happening at the center of galaxies, at least some of them. We'll generalize that into active galactic nuclei. I'm going to figure out how to say that by the end of the class. We're going to generalize it, and then we will talk about proposed mechanisms for what could be accomplishing that. So here is a nice picture of a quasar. Come on. There we go. And quasar is a portmanteau. It's a squishing together of a few other words. It essentially means quasi-stellar object. So these were things that people were seeing out in the sky that behaved like stars, although there didn't seem to be a star associated with them. And we've kind of encountered things of this ilk when we talked about neutron stars and black holes, right? These emission sources that didn't quite fit into our conception of what stars should be looking like. So here we have actually a picture of two bright apparitions in the sky. And the strange thing is that one of these appears to be one of these we now understand, or astronomers now believe, is a star that's very close to us. And one of them is a quasar, which is 9 billion light years away. And they look very similar. And the main difference comes with the radio signature of these bodies. And we'll look at that in a second. Now, the strange thing is that these quasars had redshifts, these stellar objects that we thought were stars at first, turned out that they don't make sense as stars because their redshifts are so extraordinary. They appear to be moving almost at the speed of light, up to 95, 96% the speed of light. Extraordinary redshifts in these objects. Now, could they be redshifted for reasons other than recession? Absolutely. But nobody has agreed on those particular means by which that would be accomplished at this point. Although there's some interesting evidence that, in particular, quasars may have components of them which are blue shifted as well. And so it's not entirely understood how to untangle the mess there. And we'll get into this broadening of the lines here in a second. Oops. Come on. Sorry, guys. All right. So the first question that the astronomers asked was whether the quasars themselves fit into this Hubble law, which we'd talked about already. Because if they did, then, well, if they didn't obey it, then they might be much closer than we thought, which means that something even stranger is happening. Now, I think that the thing that won people over about this was that particularly when we put this Hubble telescope in orbit, I think this was back in the 80s, we noticed for the first time that the quasars appeared to be associated with galaxies. If not in the galaxies, they were very, very close to them. And so this reinforced the idea that these strange apparitions were actually far away and not close. Now, again, when we try to estimate distances to these very far objects, we're already a little bit in the fog, right? Because we're building our conclusions based on assumptions about those bodies in general. Now, how do we get how do we understand the part of understanding the distance of something is understanding the size of it. Part of understanding the size of a galaxy has to do with how it's rotating, and how we figure out how it's rotating has to do with how massive we believe it to be. But how massive we believe it to be turns out to be a very confounded situation in its own right, because as we know, the rotation of our galaxy doesn't obey gravitational rotational dynamics. In fact, if we want to apply gravitational rotational dynamics to our galaxy, it turns out we're missing something like 95% of the matter in our own galaxy. So either there's a lot of stuff we can't see, or the galaxy rotation has nothing to do with, well, I won't say nothing, has very little to do with gravity, right? And so if that's the case, then the size of the galaxies that we're seeing is probably completely off by, 96%? And then we're in the weeds again in terms of making our distance estimates to these things. So there's a lot of assumptions that go into all of these statements that we're using to compile these theories as we go forward. And I just can't emphasize that enough. All right, so what you can see here, in the top left, you see an image of a quasar that's at the heart of this spiral galaxy, which is a couple billion light years from us. The bottom left shows another quasar that's at the center of an elliptical galaxy about the same distance. And then the middle image shows these rotating pairs of interacting galaxies, and one of them harbors a quasar. And quasar is, of course, defined by this redshift, this extraordinary redshift. And we'll talk about interacting galaxies on Thursday, because that's a whole other interesting topic. Now, there was this gentleman, I think that's worth mentioning, who was one of, actually worked under Hubble in the same lab and was one of his students originally. This gentleman, this astronomer, his name was Halton Arp, and he noticed some very strange features about these quasars starting in 1966 when he published his first book. And his argument was essentially that many of the quasars with these extraordinarily high redshifts are actually linked to objects which by other distance determinations appear to be quite close to our own galaxy. And so his central refutation was that I think that this redshift with quasars has nothing to do with distance, actually. It has to do with something peculiar which is happening in these strange jets of material that leads them to have an intrinsic redshift, which we're not accounting for. Now, ARP essentially went down on this ship. He made himself something of a persona non grata in that community and eventually was forced out of the field. I've read his book. It's actually quite compelling. It's mostly a picture book that shows different astronomical frames with their redshifts and shows how portions of them which are actually facing us, the jets are facing us, are actually more redshifted than the other components which are facing away, which is quite perplexing if you're saying that the redshift is simply due to this Doppler recession. So there's endless discussion on the internet if you guys want to follow up on that. There's of course one camp who thinks this guy's a complete nut job, and then another camp who thinks that the white knights are the nut jobs. And so that's a fun rabbit hole to go down to if you want to. Okay. Well, let's assume if they are very, very far away, then we move on to the next part of our theory, which is that they must be extraordinarily energetic if they're this. Yeah.
So quasars have two jets on either side. They're in the center of a galaxy. Does that make them anything like black holes, like supermassive black holes, like the H star?
Yeah, exactly. So the theory that your textbook, let's say the most popular theory at the moment is that there is these supermassive black holes at the center of these galaxies, which is responsible for production of the quasar jets. So they are one and the same. Yeah.
Okay.
I really think it's unfortunate because this concept of quasar was termed as a particular instance of those jets, which is pointed right at us. Now, we were able to see those were the first ones discovered because those radio jets were pointed right at Earth. The more general concept is called active galactic nuclei, which is a hard thing to say for some reason. So in general, we're talking about active galactic nuclei. So what I was getting to is that if indeed they are extraordinarily far away, which maybe they are, and if they are, they're extraordinarily bright, which means that there is some sort of process at the center of galaxies which is capable of emitting energies beyond anything that we have any familiarity with in our own galaxy, right? So it's not thought that our own galaxy has anything like this going on per se. We don't have the same sort of energy output from the center of our galaxy. Now, some people have argued that traces of material in the halo above and below our galaxy indicate that this may have happened in the past. So it's possible that galaxies go through cycles of having quasar activity, active galactic nuclei, and then they calm down and so forth. There may be some cyclic nature to this, but of course, if it did happen, it would be happening on timescales that would make it completely inaccessible to our own observation. Okay. I think that at this point I just wanted to throw this paper up here because if you want to follow up on it, this paper gives a good outline of all of the anomalies to redshifts that cannot possibly be due to recession velocity, particularly in quasars. So there's undeniably, just to at least support Halt and ARP a little bit, there certainly appears to be some subset of quasars which have intrinsic redshifts to them that cannot be recession velocities. And that's, I think that's beyond the scope of what we're going to have time to get into today. But it is something worth following up on because I think that there's very little, and I've talked to a lot of astronomers and a lot of cosmologists recently. There's literally no one who is trying to produce redshifts in a laboratory on Earth through a means other than Doppler shifting. Although we know for sure that there are ways that redshifts occur without Doppler shifting. And so if anybody wanted to have a big shining career, I think that a great place to begin would be to set up a laboratory where you can examine what sort of interactions can cause redshifts other than Doppler shifts. And there's certainly no end of calls for action. Here's another paper. And the basic idea is that, we think that even though there is an intrinsic blue shift in some of these quasars, that we can separate that out because we look at the broadening of the spectrum, right? If there's a squishiness between some of it being blue, some of it being red, well, it's going to appear wider. And so the hope is that we can deduce that as a result of it, but it's unclear how productive that has been. Of course, we're getting into deep abstractions again when we're considering the extraordinary distances. All right, so one of the important pieces, of course, in gauging distances has to do with how big something is. And the basic method that people use to understand the size of quasars has to do with the travel of the light from one side of the quasar versus the close side of the quasar, the distant side versus the close side to us. And the idea is that it has a pulse of light. It has some length of time that it's emitting characteristically, and that pulse reflects the fact that as it gives off a burst of light, that light is taking a little bit longer from the other side of the quasar versus the near side. And as a result of that, we can subtract the light years, the distance in time that light would travel, and it gives us some estimate of the width of these bodies. So, this image is from your textbook, and it basically says, okay, like assume all these stars are in this cluster, it's 10 light years across. Well, if say this star at C is this star at C is going to take characteristic length of time, the star at A is going to take less time, and therefore you can get the span of these bodies. Now, when we do this process on quasars, what do we come up with? Well, the distances turn out to be extraordinarily small, actually, which was, again, very, very puzzling because we're talking about distances on the order of maybe the size of our orbit around the galaxy, maybe even smaller, maybe the size of our solar system. All of this energy that's being outputted from these galaxies is coming from a really small place. And as we fine-tune our observations, we realize that it's coming from the actual nuclei of these galaxies. So again, more evidence that there's extraordinarily energetic events occurring in a very tiny place. Now, there is some other pieces of evidence that go into this as well. These jets were beginning to be resolved, and people were looking at the speed of the particles in these jets, right? And again, these things are moving at really ridiculously high speeds, particularly moving, at speeds that are moving into relativistic speeds. They're moving at speeds at which we would expect for some of the they're kind of exceeding the inertial capabilities of themselves. So they're under such extraordinary strains due to reacting against gravity at those speeds that they're being ripped apart into all sorts of interesting forms. So here we have a few of those different jets and different wavelengths. And the result of this was that we found there was not one type of quasar, but all sorts of different quasars, and the different qualities of those ended up to reflect something about the properties. Well, we hope that they reflect something about the properties of those galaxies in general. So we hope that we can learn a lot about it. Now, they grouped all of these different types of jets and galaxies and quasars, again, into one concept, which we call active galactic nuclei. So now we move into the fundamental question of what could be causing these extraordinary outbursts of energy from these galactic centers. So let's look at the qualities that we're trying to explain here. They're extraordinarily powerful. They emit more power and radiated light than all the stars in our own galaxy combined. They're tiny, sometimes as small as our solar system. And they appear to be shooting out pairs of very confined jets of material at very close to light speeds in a tight beam. And they emit these jets at distances that are way beyond the galaxies that they live in. Very powerful sources of radio emissions, gamma ray radiation, which we can observe with different telescopes. But because they emit so much power from one place, there's no way we can explain that with our typical stellar processes. In other words, nuclear fusion can't pull this off. A supernova can't pull this off. There's no known process in our canon, in our wheelhouse of mechanisms that's capable of generating this much power. Now, of course, at this point, the popular idea is that there is a gravitational center in galaxies which is capable of pulling in material and causing it during that pull to be excited into a disk around it, which is in such a frenzy due to this pull of gravity by this supermassive object at the center that it stirs up all sorts of interactions amongst that material and results in the outflow of energetic particles, right? This is the sort of standard explanation. But again, I think that what we have here is another reified description of what is happening, which is being converted into an explanation. In all reality, this concept of black hole is something of a place filler for something which we don't totally grasp, right? In fact, just to remind you, the basic idea of black hole comes down to a point where general relativity stops working as a theory, if you can even call it a theory. In reality, it's more of a description of what's happening than an explanation. So at some point, the laws of gravitation, which we embrace because they work so wonderfully here on Earth, stop to make sense when you get into masses that are this large. Now, why do we think that the masses are this large? Because we don't have another way of generating this kind of outburst without having masses that are this large. We don't know any other way of accomplishing that. Although there's a couple of hints, which I'll give you in a minute. But the same thing seems to be true with the rotational dynamics of the galaxy. What could hold all of the matter together in our galaxy? Well, there must be some giant object at the center which is doing this. But again, this seems in some sense at odds with the problem that our galaxy doesn't seem to rotate gravitationally to begin with. So maybe it's not a gravitational phenomenon at all. And I think that there's some tantalizing work going on that concerns itself actually not with gravitation, but with the electromagnetic properties of the galaxies themselves. In other words, how magnetism is introduced into the galaxy as a whole and what that could do to confine energetic particles and interact with them. So hold on, I'll get back to that in a second, because this is a really interesting point. But, you know, again, your textbook writes your textbook writes, it was only as proof of the existence of black holes accumulated over several decades that it became clear that only supermassive black holes could account for the observed properties of quasars and AGNs. Okay. Well, certainly there is evidence that there's something crazy happening at the center of galaxies. I think actually the evidence that it is gravitational is extraordinarily weak, unless we're willing to entertain the idea that there's 96% of the matter in our galaxy is invisible, which is a difficult pill to swallow, at least for me. You're welcome to make your own conclusions. Okay, so in order for scientists to justify this idea that there is a breakdown of physics at the center of the galaxy, they have to demonstrate that a ton of mass is crammed into a volume not much bigger than, say, our solar system. Now, of course, this is done with these Doppler shift rotation dynamics, right? But I think I've kind of beat on this horse enough that the rotational dynamics, of course, don't actually tell us about the mass of our own galaxy. So I think that it's a little scary to build our entire theory off of rotational dynamics, but it's worth presenting that that's what's happening here. So, and this is, of course, we can, of course, get these rotational dynamics. We can get these redshifts. We do see that the galaxies are rotating, and we extrapolate their mass backwards from that. We weigh the central mass of the quasar as a result of that. So this one in particular, this is the M87 galactic nuclei, and it's about, if we from the rotation of this galaxy deduce the mass of the object at the center of it, it's something like 3.5 billion times the mass of our sun, crammed into essentially a volumeless point. Okay. Now, I guess I'll mention one more thing here. The argument is often made, well, what if there was a bunch of heavy stuff there, right? What if there was a bunch of stars at the center? Actually, we can't really see the center of our own galaxy or any center of any galaxy very well because there's actually tons of stars all around it. It's the brightest point in the galaxy is this bulge at the center of it. Well, the argument is generally given that if there were a bunch of stars there, that they would be crashing into one another, and this would be a completely unstable structure. And all of this, again, is founded on abstracted theories, which are built on other theories, which are built on other theories, to the point that the entire conversation is constrained to the concept at this point that the universe had a beginning, first of all, which is completely theoretical, and that the beginning occurred about 14 billion years ago, which is entirely too short for things to have cooled off to become cold and invisible. Again, if for some reason society flip-flops again and embraces something approaching a steady state cosmology, then the time available to make objects, to make large, cold objects is actually within reach again. And so who knows? Perhaps the things that we call dark matter are there. Perhaps there is a lot of material there, but it's invisible to us because it's very, very cold. Yeah.
Why don't scientists plug on to the Big Bang Theory?
That's a really, really, really hard and good question. And I hope that I can answer it by the end of next week. So I think that, so something really interesting happens in engineering that doesn't happen in science. So, I have a lot of family in the Bay Area. I spend a lot of time down there. And the Bay Bridge, which goes from Oakland over to San Francisco, was falling into disrepair. And so they decided we have to build a new bridge here. And what they did was, instead of knocking the old bridge down, and then everybody is completely screwed because they can't get to San Francisco, they built a bridge next to the old bridge. And they did that for several years. And once the new bridge was built, then they knocked down the old one. And I believe that you're right. And I think we'll see that the standard lambda CDM cosmology is in dire straits right now. And I think everyone recognizes that. I think literally everyone recognizes that. However, nobody has proposed, nobody with the right position in the world has had the ability to propose a model which is equally satisfying. And so Fred Hoyle was a very, very well-respected British cosmologist. And Fred Hoyle, while he was alive in the 20th century, had actually captured a good portion of the cosmological community. And this really doesn't come across in your textbook, which I think is a bit of a tragedy, but I would say that the majority of maybe I'm going too far there. A lot of the cosmological community did embrace a eternal universe and a steady state cosmology through most of the 20th century. So this piling on the Big Bang was really a product of the CMB. And I think we have to really analyze the CMB to understand fundamentally what we're seeing in the CMB, and then to make up our own minds as to whether it is in fact cosmic or not, because that's really what it comes down to. And so, we're going to have a lot of fun with the CMB because there's some really interesting proposals about what this radio source could be. I'm actually trying to build a radiometer right now. If anybody wants to help me, come talk to me after class. So, without completely getting off the rails here, we'll do the CMB in great detail, but the CMB detection is one of those very interesting events where it was actually first detected on Earth. And actually, measuring infrared signals on Earth, we know is absolutely impossible. I won't say impossible, but extraordinarily difficult. In other words, every time I show you an infrared picture of a galaxy or something in this class, it's coming from a satellite that's in space that has huge heat shields on it, right? And the reason for that we put them in space is obviously because it's cold out there, so infrared, so measuring heat is a lot easier when you're cold, but also because our own Earth has a great deal of energy in the infrared, right? Particularly the waters of our own ocean, particularly the atmosphere and all of these things. And actually, if you read the analysis of the gentleman who first announced the CMB discovery, their horn that they used this antenna to make this discovery with, was constantly plagued by the introduction of water into the measurements. And something that people don't really realize until you start to tear apart the experiments themselves is a very interesting phenomenon occurred here, which is not too different from our distance ladder situation, which is that we have these beautiful maps of the CMB, which you've probably seen. These big, they look like globes, it's basically the whole night sky. What's really fascinating that most people don't understand about those maps is that they were calibrated based on already assuming what the CMB looked like in the first place. So they took the frequency that they were looking for, and they used that to go and scour the sky for this artifact. Now, let me give you this is very difficult. I always want to use like an audio engineering analogy for this, but let's say I have, I don't know how to do this. Maybe you can imagine if I wish I had a guitar amp with me here, I could show this to you a lot easier. But if I had a guitar amp here and I just played white noise through it, right? And let's say that I took one channel, let's say I had a really nice EQ on it and I could boost like 1,000 hertz on it of that white noise. And I just turned up 1,000 hertz of it. What would it sound like? Well, eventually it would sound like a pure tone of 1,000 hertz. And I could say to you, hey, I went looking for the sound of a B flat in this noise and I found it, because there's definitely a B flat there. And there is. And in fact, I could do that with every note in the scale for you. I could pull it out of that noise. So the problem with knowing what you're looking for when you go looking for it, and particularly building devices that are capable of detecting that, is that you're kind of married to your conclusions in advance. And so I'm going to pull that apart because this seems like a wild accusation, but I think that there's good reason to believe when we look at the build out of the radiometers that were used in space, particularly the WMAP project, that there's something a little interesting going on there. And that in fact, I think there is reason to at least crack open the conversation of whether the CMB deserves the C in front of it in the first place. And so we'll tear all that apart very soon. But just to sort of preview it, because I feel like I've almost said everything I can say about active galactic nuclei. So, you're gonna hopefully you're all reading the textbook as well, and the textbook will of course do a great job of elaborating on this paradigm even better perhaps than I'm doing today. But the basic mechanism here, which I kind of broached already, is that if a gravitational source, some exotic form of gravitational matter, like this black hole, is producing the AGN, the quasars, then the mechanism responsible for that, and really no matter what is producing it, this mechanism is pretty much the only thing that I can even think of that makes sense too, is that there's a great eddy, a great torrent of material that's in motion at the center of the galaxies, and the friction between those different, I don't even want to call them atoms because in many cases they're probably ripped apart, but the frictional interactions of those are what lead to the excitations and the emissions that we see. So it's something like your textbook gives the example of the spacecraft during reentry, right? Where it's actually colliding with the molecules in the air and ionizing them, and you get this great glow of material. So the idea is that something similar to that is what's happening. Now, like I said before, our own galaxy doesn't have this, doesn't have a quasar, but we do have some bubbles of excited material above and below us. And this leads us to the conclusion that perhaps this may have happened in the past. And who knows, maybe it'll happen again in the future. I'm not going to even go into this. This is a breakdown of the tightening. So as there's more material in this disk around the center of the galaxy, it constricts the emissions from the actual point source there. Oops. Okay. Now, when I try to think about okay, if dark matter is not the solution to the galactic rotation problem, if something else is causing our galaxy to stick to itself, and I mentioned a couple of ideas to you before, I actually mentioned only one idea, which I had just been discussing with this Princeton astrophysicist over the weekend before, which is the fact that all of our solar systems appear to be in contact with one another, right? They appear to be enmeshed with one another to some extent in so much as our heliosphere, right, the bubble of material that separates us from interstellar space, appears to extend all the way out to the next solar system. And so there's some sort of chaining together of these, right? And so I proposed it to him at the time too, and I proposed it to you guys that perhaps there's some sort of Velcro happening between all of these star systems, which holds them together as well. I don't know if that's the case, and he doesn't know whether that's the case either, and no one does really. But it is something very new that we're realizing as we study our own heliosphere, and we know nothing about any of the other star systems' heliospheres, so the best we can do is assume that they're somewhat similar. But it is more or less understood that our own solar system, if we consider the Oort cloud, the cold debris from which our comets originate at the farthest reach of our solar system, it's almost exactly halfway to the next star system. So there must be some interaction between the star systems. Now, another possibility that I want to bring up to you today is that the galaxies themselves have an appreciable magnetic signature to them. Now, this has been largely ignored because it's not a simple magnet, right? It's not a simple, and I don't think that, unfortunately, I don't think we've had much time to talk about how magnets work in this class. We did last semester a bit. But, the simplest magnet you can imagine is actually an individual atom, particularly an ionized atom that has some conductive qualities to it. And I think that, did we talk about spin 1/2? We did in this class. I showed you some modeling of what that could look like in an atom, right? Sort of one way to think about spin 1/2 is that as the atom is twisting around, that it's also involuting inwards, right? This is one way to think about it, at least a way to visualize it. Now, if the atom's conductiveness has to do with its rotational dynamics, its spin, its charge emerges as a result of this, then magnetism can be thought of as the lateral effects. So how the atoms equatorially interact with one another when they're in this conductive state. Now, if you take if you try to imagine the most simple magnet that you can possibly conceive of, An easy way to do that is to take you can imagine a single file line of atoms that are all in contact with one another. This is just purely hypothetical. Of course, real wires are a lot more complicated than that. They have very complex orbitals. They're very heavy atoms, right? But if you take a very simple atom that's just a simple S shell like a hydrogen, you string them all in a line together, you can get a conductive phenomena amongst it, right? You can conduct electricity in this, right? In other words, their surfaces are all engaged with one another and they're conducting this motion along the line. Well, it turns out that wires also in this way produce that magnetic effect laterally. So they're going to be interacting with each other on their sides as well. This is what magnetism is. Now, if you curl that wire into a loop like this, what you do is you create the most primitive form of an electromagnet, because what you've done when you take a wire and you curl it so that all the ends of it are all stacked up like this, is you put all of their equators in a line together, right? So their equatorial motion, their magnetic moment is all aligned perfectly. And you make something of a big toroid out of it, where the motion of the outer shells of those is batting inwards into the inside of the torus. Now, what people have started to realize when they're looking at galactic magnetic fields is that the spiral arms of the galaxies, the individual wings of the galaxies, also seem to have a bit of this same magnetic quality. But because the arms are, in some sense, not stacked on each other, but they're in a plane, the overall magnetic field is somewhat neutral, right? If each one of these arms has an appreciable magnetic moment to it, but they're side by side instead of stacked in a column like a solenoid, you don't really get an overall solid magnetic field. And so the magnetic interactions, I think, have been, well, it's certainly a very interesting topic of research right now. And so, this is a highly simplified picture of, let's say, the magnetic field around like a nascent star system, right? It's very concerted. You have a single toroid, and you can imagine the magnetic interactions, the way these atoms are moving, that their shells are moving, it's all batting inward, and that's all well and nice. Galaxies, of course, have concentric spirals of these, which are oftentimes in conflict with one another. And so it's very difficult to appreciate how strong of an influence these magnetic processes may play in the end. And so there's been some really exciting work. This is one paper. Oh, I put it upside down. How about that? Whoops. But what this paper first proposed was that actually each one of these spiral arms has conflicting helical magnetic fields to them. So you can think about each arm of the galaxy as its own little solenoid system. And this is fascinating because what it means is that the magnetic processes could be actually quite significant players, not only in the cohesion of our galaxy, but also in terms of focusing the beam of energy at the center of the galaxies. So you guys most of you are probably too young to even remember the old TVs, right? These huge, heavy things that would sit, and they had this big tube system inside of it. And the way that they worked was they used magnets to focus a beam of ionized gas at the back of the screen on some phosphorescent thing that would glow when it was struck with this beam, essentially, when the beam was aimed at it. This is essentially the same process which is playing out. Well, it's not the same process. I'm proposing that there might be a similar process playing out at the heart of galaxies as well, because while it's quite apparent that there are tight beams of energy and that the energy must be in some sense produced by frictional interactions between all of the atoms that are swirling around the center, the question of what focuses it may have a solution in the magnetism as we come to understand the magnetic properties of galaxies further. And so I wanted to just take a moment to crack that open because unfortunately your textbook's not going to get to it. So if you do want to follow up on some of these feedback processes, which are at the edge of what's known, there's a great textbook here. It's called Cosmic Magnetic Fields. This is by Keppins and Porth. And yeah, there's a lot of food for thought there. So we'll pick up there on Thursday. You guys have a great week. See you then.